Okay, this is chapter 2, part 1. Let's jump right into our PowerPoint notes here. The first one goes like this. A central aim of statistics is to represent and simplify data with a mathematical model that predicts an outcome variable with independent variables. So just to remind folks, a couple of things here, that when we say simplifying data, actually I think it'll help us if I skip forward a little bit to a visual of something that we're talking about here. Here I have a graph that shows both an x-axis and a y-axis, and you could put in whatever variables you want. What you're looking at here is a relationship between two variables, and let's say that it was two along the x-axis. Let's say it was a test that students were given, and let's say on the y-axis it was like a quiz that was maybe worth 20 points for the quiz and 60 points for the test. And you're looking to see the correlation between those two. Do students who performed well on the test also do well on the quiz? And so each one of those blue dots is an individual student and their two scores, where those two scores line up on the graph. So for example, if you can see hopefully you can see my arrow there. You have this one student right here who looks like they got close to 30, a little bit under 30, maybe 28, 29 on the test, and then got like maybe a 6 on the quiz. And so because they scored those two scores, then they get located right here. And all these other blue dots would be other students and how they fell here. I don't know how they would have gotten negative numbers over here. So again, this graph is not a perfect example. But so there's a couple of things that are going on here. You have what we're trying to do with statistics is we're trying to summarize all of these students, in this example, all of the student scores as simply as possible. And so you can see that you simplify this by coming up with a line, and this line actually is like algebra. It represents an equation that that summarizes your data. You're reducing the data down to an equation, which will help you be able to predict somebody's, in this case, quiz score based on their test score. So this line, statistics, the process statistics will create this line or this equation that's in red here, and so that line will say that we'll make the prediction. Let's say that you got 20 on the test. We go straight up there, and it hits the line about here. So this line, another word for this line is equation, which I've already said. Or you can also, another word that gets used for this line is model. So according to this model, if you got 20 points on the test, this model predicts that you got about 8 points, or maybe a little bit more than 8 points on the quiz. Now, maybe that's not a perfectly accurate prediction of what you actually did score on the quiz, but this is one of the things we do with statistics, is come up with a model, an equation, a line that can predict what the value is for you on the dependent variable, the outcome variable, based on what you scored on the independent variable. In this case, the independent variable is the test, right? So you're trying to predict one thing from the other, and your prediction will be off a little bit, but that's one of the purposes, the goals, the aims of the scientific method, is be able to, based on data, to predict whatever it is that you're trying to predict. So that's just going back to this original point. That's what we're getting here with this central aim of statistics, is we gather data together, people's scores, we come up with a mathematical model or a line, if you want to think of it visually, a line that predicts one variable from another, predicts your quiz score from the test score. That's what we're trying to do. It's all about reducing actual information, actual data, down to a prediction line, a prediction. And we do that all the time. Lots of different ways. You'll learn that in this class. Although the models will never perfectly reflect the data, we want them to fit the data as accurately as possible. So if we go back to that picture, the visual again for a second, the line says that if you get a 20 on your test, that you're supposed to get a around a little bit over 8, it looks like, on the quiz. So let's say that this one here, let's say that this is 20. This person, it's a little bit off, but let's say that this was 20. This person gets a 20 on the test, and so this is where they're at. So since they got a 20 on the test, the model predicts that they got a little bit over an 8 or something on the quiz. That's what the line says. But the truth is that the student actually scored here. This is the reality, that they got a little bit lower than that, a little bit under 8, score of 8 on the quiz. See, because their dot's a little bit lower down here than the line. So the truth is that they didn't do as well as that line would have predicted that they were going to do. So that's an example of how we're never going to have a perfect prediction. The data does not give us perfect predictions. It gives us predictions with a little bit of error. And you can see that as long the only way you could have a perfect predictive line that was perfect fit to the data was if all these dots were a perfect line. If all these dots were a perfect line and they were all sitting on this red line from top to bottom, perfectly sitting on that line, then you have a perfect prediction line, because in every instant with every student, they get what the line predicts that they should get because they're sitting right on the line like they're supposed to. But we can see here that most of these dots are off the line, which shows that the predictions are not perfect. They're in the neighborhood, they're approximations, most of them are a little bit close to the line, but there's error there. So that's what we're getting at with this earlier point, that your models, the lines that we come up with, the equations, are not going to predict things perfectly. But they're going to give us approximations. And some models will be better than others too. Some models will get us a little closer to accurate predictions, and some models will be a little bit worse. So that's where we use this term fit. That if the line that you come up with is real close to all of those dots, real close to the data, then we say that model fits the data well. It matches up with reality pretty closely. If those dots are all over the place and far away from your line, far away from your model, then we don't have a model that fits the data well, because the data are just all over the place and far away from that line. And so our predictions are further off. There's more error in our predictions if you have dots all over the place, not sitting close, not falling close to that line. So hopefully again, this stuff's a little challenging sometimes, but bear with me step by step. This should get gradually clearer and clearer. So we say a model has a good fit if it does a good job predicting the outcome. Remember that with my example, the outcome is what you got on the quiz, from the values of the predictor variable or independent variable. And in my example, the predictor variable is what? Remember, it's what you got on the test, right? You're using the test score to predict your quiz score. If it has a quote-unquote moderate fit, the model's prediction will be off to some extent. And what you find most of the time when we're studying human beings, because they're so complicated and hard to predict how they're going to behave or how they're going to do, usually our models in the social sciences where we study humans do not have a great fit. At best, maybe a moderate fit, not a strong fit. You get a strong fit in the hard sciences, chemistry, physics, that kind of thing. But you do not get a strong fit with most of the time when you're studying humans, because we're just not that simple. We can't predict people's behavior that accurately. Now, another important thing, linear models. These are models based on a straight line, where we assume a stair-step relationship between the independent and the dependent variables. So, for example, I list here an example. For each additional year of school, our model predicts that you will earn an extra $2,500 per year in income, how much you earn on your job. So if we were to listen, so you're asking, well, how do you come up with this? Again, you do like a survey, a sample of people, and you say, okay, uh, how many years of school have you completed? 12 years of school, that's finishing high school. 16 years of school, well, you're probably finished your bachelor's degree. So we could ask you how many years of school you completed, and then we can ask you in the past year how much income you earned. And then we can go back to this graph and we can plot out your income and your years of education. So uh, we would put your years of education along that x-axis there, somewhere between, you know, 1 year of school, and nobody only goes to kindergarten or first grade, but you know, we'd have a scale that goes up, you know, 1, 2, 3, 4, 5, each being how many years of school you completed. Then on the y-axis would be like thousands of dollars that you earned or something like that. And you would get it, each person in that sample would get a dot on this graph, which was coordinated with how many years of school they completed and how much they made that year. And then we would use statistics to come up with a line which would represent how much, you know, would be a prediction line, a model of how much you earned based on how many years of education you had. And the point we're making right now is that that line would be straight. Typically, uh, just almost without exception this semester, the statistics that we will learn will be based on a linear model where we come up with a prediction line that is a straight line. That, and what we mean by straight line is, just like I was using that example, when it's a straight line, what that means is for each extra year of school, you're going to get that an extra amount of money. That's what the prediction says. And that extra amount of money is going to be the same from 1 year of school to the next year of school to the next year of school to the next year of school. So if you went 13 years of school instead of 12, well, then you get an extra $2,500. According to the model, it predicts you're going to make an extra $2,500. If you did 14 years of school instead of 13 years of school, then we're going to predict that you got an extra $2,500, and so on and so on. The same, $2,500 extra dollars for each additional year of school that you completed, right up the stairs, right up the chain there. That's a linear model that says that you get the same boost, the same, in this example, the same amount of money uh, with each additional year of school, and it never changes. Whether it's 10 years of school or 20 or 30 years of school, stay in school forever, you're going to get, for each extra year, the model says you're going to get an extra 2,500. What you see here is I also added a graph that is a curvilinear model, which we will not be focusing on this semester, but I want you to be aware of it, that there are more sophisticated models which do not assume a stair-step relationship. They don't assume that every step up in your independent variable is going to mean the same step up on your y-axis, right? In this case, you see this example here that I found is along the x-axis, you have the BMI, which is a measure of sort of how heavy you are, where it looks at both your weight but also your height, because taller people tend to be heavier. So it kind of adjusts for height. So it's a measure of weight. And then on the y-axis is your percent body fat, how much of your weight is in fat versus muscle, bone, etc. And so what they found with this data, each one of those red dots is a person who's in the sample, and they measured that person's BMI, their weight, and then they also measured using some sort of technology what percent of fat that person has in their body, ranging, as you can see, from 15 on the low end up to 40, like 45% on the high end. And what you see is in those dots again, each dot represents a person and where they fall on those two. And what you see is as you get heavier and heavier people, you move to the right on that x-axis. The percent fat does go up. Follow this curve here. It does go up. People do have, if heavier people do have a higher percent of fat in their body. But it's not linear, it's not a straight line. It curves. So what it means is gradually it flattens out a little bit. The heavier the people, yes, they keep going up in percent body fat, but they go up more slowly at the higher end of weight here. See, they in the beginning, if you go from people who have a BMI 15 to 20, as you go up 1 in BMI, the percent fat jumps up quite a bit. The line here is fairly steep. It's fairly steep. But the further you go, the more that line flattens out. It's still going up, but not as steeply as down here at the bottom. That's an example of a curvilinear relationship. And sometimes real life works like that. I mean, this is real data here. And so what they find is as you get heavier, people get heavier and heavier. Yes, their fat content in the body goes up, but it doesn't go up like a stair step. It's not a straight line. It goes up, but it goes up slower and slower at your higher and higher levels of weight. That's what that curvilinear line is telling us. And again, I wanted to introduce this idea, but we will not be figuring out the statistics to be able to come up with curvilinear lines. That's a little above our pay grade. That's a little too sophisticated for what we'll be doing in this class. We're going to stick to these simpler linear models because they're mathematically and conceptually a little easier to handle than curves. Curves are a little more advanced. So linear models is going to be the focus of this course. Okay, let's see. We're now 16 minutes into the video. That's probably a good place to take a break and start again with part 2.